So how do we decide what kind of reaction can occur? And here at the end of the eliminations, we start talking about substitutions also, and we're going to compare the two reactions and decide what can happen. And in the first one, we see that we have a tertiary leaving group, T-butyl iodide, and we added sodium methoxide, which sodium methoxide is just a strong base. The rest of it doesn't matter. So we can forget about the sodium, it's unimportant, and with the strong base, all we can do is grab the hydrogen off of the adjacent carbon, form the double bond, kicking out the leaving group to form the isobutylene. And that's because we have the strong base and the tertiary compound. Here in the second one, we have a tertiary compound. We see that we have water. It's a weak base, weak nucleophile, polar protic solvent, so it's going to form the cation first, and then from there it can go on to form either of the two compounds, and it will compete between the isobutylene and the T-butanol. So to get to the isobutylene, what happens is the water grabs the hydrogen, we form the double bond. We can also redraw the same cation, and we can see the water adding to the cation to form the protonated T-butanol, and then we can have water come in and grab the extra hydrogen, and we can form our second product. So both of those can form from going through the same intermediate of the cation, and we just have to, the conditions of the reaction will tell us which one the reaction will prefer. And over the next 4 or 5 pages, we'll talk about each of those. And on this page and the next page, we have the things we need to look for to try and decide what can happen. The first one we want to look at is the nucleophilicity, and how good of a nucleophile is it. If there's a negative charge, it'll be a much better nucleophile than if there isn't a negative charge. So water is a weak nucleophile, but hydroxide is a much better nucleophile. The second thing we want to look at is polarizable. If the atom is larger, you have a better opportunity to distribute the electron density around the atom, so it's more polarizing, and the more polarizing it is, the better the nucleophile is. So sulfur is a much better nucleophile than sulfur, and hydrogen sulfide is a much better nucleophile than in water. Remember what we learned earlier in the beginning of work 1 about how strong a base is compared to its conjugate acid. So the pK for water is roughly 16. The pK for a carboxylic acid is roughly 5. So we know the stronger acid has the weak conjugate base, and the weak acid has the strong conjugate base. So we need to remember our pKs and how acid-base works. So on the bottom of the page here, we have how we can think about things, whether they act as a nucleophile only, a base only, or a strong base, strong nucleophile, or a weak nucleophile, weak base. So the list of nucleophile only compounds are shown here. They are not strong bases. They won't pull off a hydrogen very well. Whereas then we have the base only list. They will primarily only act as a base, pulling off the acidic hydrogen to form the alkene. And then we have strong base, strong nucleophile, where it can act as either a base or a nucleophile. And then we have the weak nucleophile, weak base, listed on the last box here. And these we need to keep track of, remember those, come back to this page as you're working problems out the back of the chapter, or come back to this video as you're working problems out of the chapter, and think about what we talk about on the first few slides of this video. On the next page, we have the things that are a nucleophile only. If you have a primary leaving group, it's only an SN2 mechanism. If you have a secondary leaving group, it can be either SN2 or SN1, and if you have a tertiary leaving group, it's only going to be an SN1. With a base only, they're easy because all three of them only form an E2 elimination because you have the strong base. There's nothing else that can happen with those. On the next page, we have strong base, strong nucleophile, and on this page, we end up with a lot more possibilities. With the primary, it could be either an SN2 or an E2, where the SN2 is the major, the E2 is the minor. With the secondary, you get a whole bunch of both, with the major one being the E2 elimination, but the SN2 happens some. And then with the tertiary, all it does is an E2. With a weak base, weak nucleophile, the last one here, the primary is not very practical to give you either the SN2 or the E2. A secondary is not very practical but can give you any of the four possibilities. And then the tertiary gives you a split of the substitution and the elimination. And we know the difference between what can happen based on the other conditions of the reaction for all of these. So here's the page we've talked about before, the guidelines from the substitution and here in the elimination chapter and how we tell them apart. So we have a strong base, strong nucleophile. It goes either SN2 or E2. The weak base, weak nucleophile goes SN1 or E1. Primary halides are primarily an SN2 mechanism, with once in a while being an E2 if we have a bad nucleophile. And by the bad nucleophile, which we'll say again lower in the page, T-butoxide is a great bad nucleophile but a strong base. So with the primary halide, the main product will be the elimination. Tertiary halides with a strong base has to be an E2. If there's a weak base, it'll be either an E1 or SN1, depending on what we have in the reaction. Secondary halides, they're no man's land. It can be anything depending on what we have. If we have a strong base, strong nucleophile, it's going to be an SN2 or an E2 product. With a strong base, strong nucleophile, it has to be a 2 mechanism. With a weak base, weak nucleophile, it has to be a 1 mechanism. And the good ionizing solvents, the polar aprotic solvents, favor the 1 mechanisms, as we see in part E down here, where polar aprotic solvents favor an SN2 mechanism. High temperatures favor elimination, and some bases favor substitution. Small favor substitution, whereas large favor elimination. And this page is very important, and it's a breakdown of everything that you need to know for this test, what can happen. So you got to keep track of what the possibilities are as you're going along. So then we have the regiochemical outcome and stereochemical outcome for each reaction. If it's SN2, the nucleophile attacks the alpha position, the carbon where the leaving group is connected. And for the stereochemical outcome, the nucleophile replaces the leaving group with inversion of configuration if you have a stereocenter. With an SN1 reaction, the nucleophile attacks the cation, the carbon where the leaving group was, so it's connected in the same fashion as the starting material. With the stereochemical outcome in an SN1, you end up with a racemization of the configuration because you go through that planar cation and the nucleophile can add from either side. In the E2, the regiochemical outcome, the Zaitsev, the more substituted product is favored over the Hoffman, the less substituted product. The exception is if we have a sterically hindered base, then the Hoffman product is favored. And in the E2, the process is both stereoselective and stereospecific. When applicable, a trans disubstituted alkene will be favored over the cis. And when the beta position of the substrate has only 1 proton, the stereoisomeric alkene resulting from anti-coplanar, anti-periplanar elimination will be obtained exclusively in most cases. Okay, and I know there's a lot in here, and it's just summing it up in a different way than what we said on the last page, getting to make sure we know what kind of stereochemical or regiochemical outcome to expect. And the E1 product is the Zaitsev product is more substituted, as always favored over the Hoffman, the less substituted. This process is stereoselective. The E1, when applicable, a trans disubstituted alkene will be favored over the cis disubstituted alkene. Okay, so as you're working problems, think about the last 4 pages or 5 pages of this video and look at these as you're going along. And remember, you have all of these in the PDF that I've shared with you in class. So you have this written out along with what's in the YouTube video.